Okay, so I am beginning module 3 on the standard linear model and logistic regression, which is what I'll be using for the generalized linear model. Okay, so what is logistic regression? So it's a statistical method used to analyze a relationship between a binary dependent variable and one or more independent variables. So the dependent variable, as I said, is binary, so it could be either yes or no, 0 or 1. And the independent variables or the predictors are continuous, or they can be categorical as well. So it's a type of generalized linear model that uses a logistic function to model the probability of the dependent variable being a certain category or level based on the values of the independent variable. Um, so the goal of logistic regression is to find the best model that describes the relationship between the dependent variable and the independent variables. The logistic regression models the probability of a binary outcome, since that's our dependent variable. And the output of logistic regression is typically expressed in the terms of odds ratios, which helps to interpret the effect of each predictor variable on the outcome. Okay, so moving on, logistic regression. So what's the difference between logistic regression and the linear model? So they both analyze the relationship between dependent variables and independent variables. The standard linear model assumes that the relationship between a dependent variable and the independent variables is linear. So that means that a change in the independent variable results in a proportional change in the dependent variable. The GLM allows for nonlinear relationships between the dependent variable and the independent variables. The linear model assumes that the errors or the residuals are normally distributed. That's one of the assumptions, whereas the GLM allows for a variety of error distributions, such as normal distribution, binomial distribution, etc. It just depends on the nature of your dependent variables. And the interpretation of the coefficients in the linear model are very straightforward. They represent the change in the dependent variable for one unit of change in the independent variable, holding the other variables constant. But the GLM, the interpretation of the coefficients really depends on the length function and the error distribution. So in summary, the linear model is a bit more restrictive, and it assumes linearity and normality of errors, whereas according to Press and Wilson, the GLM is a more flexible model that allows for nonlinear relationships and a variety of error distributions. All right, so let's take a look at the data that we're going to be using and what types of variables that we have. So first we have our dependent variable, or our outcome variable, and that is being quote unquote healthy. And this translates to the absence of seizures. And the opposite end of this is unhealthy, and that would be the presence of seizures, so somebody having seizures. Another variable is the EEG being within normal limits. This is our continuous independent variable. It takes account the test results of an EEG and the score of WNL, or within normal limits. That's the outcome of these tests would be, we'll turn the outcome of these tests into a numerical value. Low numbers would indicate abnormalities present in the EEG, and then higher scores would indicate more normal, within normal limit EEGs. Lastly, we also have our categorical predictor, which is medication compliance, and this is divided into 4 levels. So 1 would indicate non-compliance, 2 would indicate minimal compliance, 3 is moderate compliance, and 4 would be fully compliant to taking their medication. I do have another variable that I sometimes use in my data. It's a binary predictor, and it's a continuous predictor, and it is just age. So we can see that we've got a continuous variable and a categorical variable. So in order to be able to compare these two, we have to code our categorical predictors. So what does that actually mean? So what is coding of categorical predictors? So category predictors need to be coded or encoded in a way that regression models can understand them. So we can transform these variables into numerical values that can be used as inputs in a regression model. So there's multiple types of ways to code your categorical predictors. I'm going to talk about dummy coding, effects coding, and contrast coding. So dummy coding is our most common type of coding, and what it does is it creates a separate binary variable for each level of the categorical predictor. Unweighted effects coding is similar to dummy coding. However, the difference is in the way that they reference their variables. In dummy coding, the level of the categorical variable is implicitly used as a reference category. So usually that's the first level. While in unweighted effects coding, the reference category is the mean of all the levels. We've also got some weighted effects coding, and that is when the coefficients are weighed by the number of observations in each level of the categorical variable. This type of coding can be useful when there's like some large differences in sample sizes between the levels of the categorical variable. The weighing ensures that the estimates for each level are based on a more representative number of observations. And we've also got some contrast coding, which creates a set of variables and compares the means of each group to some reference group. There's multiple different types. There's like sum contrast, deviation contrast, Helmert contrast, etc. So let's do this with our data. So I picked dummy coding because we have a categorical variable of 2 or more levels. So that's why I picked it. As I previously mentioned, our categorical predictor is medication compliance. So that's denoted in the chart here by non, min, mod, and full. I use the contrast function in R to convert my category predictors, and this little thing is what I got. So vertically, there are 4 categories: non-compliant, minimal, moderate, and full. And then horizontally, we have a k minus 1 of the variables. So in this case, that would be 3. So we can see that non-compliance is eliminated here because here as the first variable, because it's implicitly used as our reference category. And that's usually how dummy coding works. All right, here we go. So the standard linear model, I just kind of wanted to try the linear model with our categorical predictor. I just ran a quick linear model just to see the relationship between our compliance medication levels. They're significant predictors, really, for the most part, looking here at the p-values. The exception would be the minimum compliance over here. It's larger than the 0.05 level. And for the sake of time, we're just going to address a few of these diagnostic plots. So the scale location plot helps us check the assumption for homoscedasticity, and it's showing us that there are some potential outliers that may be causing heteroscedasticity. It might relate to our minimal compliance categorical variable, considering it's not a significant predictor at the 0.05 level. But I'm really not surprised to see some funky, diagnostic plots here, considering we're visualizing variables that have multiple levels within them. So kind of assumed it would get a little bit funky looking at this normal QQ plot. There's definitely some changes around the tails and a lot of residuals that are kind of skewing the data a little bit. Okay, so then I decided just to do the linear model with using all of my variables, not just my categorical predictors. So what we can see here is that age, compliance of medication, and EEG results have a positive correlation with our outcome variable of seizure absence, or quote unquote healthy. Our p-values indicate statistically significant predictors for the most part, with the exception of age up here. Shifting over to our diagnostic plots. So we've got a QQ norm plot over here. It looks relatively normal. There's some slight deviation at the tails. Our residual versus leverage plots show the presence of a few variables that might be influencing our data and might impact our regression coefficients. So they may be outliers, or they might just be errors in the data, or they could be real. So we would have to further inspect our data and clean it up to see what this means. Um, so what we're going to do is take a look at what our data does when we use a logistic regression model. Okay, here we go. So here is the GLM model we decided to go with. All right. So first, let's take a look at our estimate values, which are right over here. The positive numbers are indicating a positive relationship between the specific predictors, so compliance at a level 4, and the EEG testing. Um, so age and some lower levels of medication compliance are showing a negative relationship between that predictor and the dependent variable. Switching over to our p-values, they also indicate that full compliance and EEG tests are statistically significant predictors at the O5 level. However, the others are not. Lower compliance and age is not a statistically significant predictor. Moving on to the odds ratio here to the right, full compliance of medication, so CMPL4 and EEG have a greater than one outcome variable, which indicates that an increase in the predictor variable is associated with a higher odd of the outcome variable. So an increase in medical compliance correlates with an increase in an outcome variable of healthiness, or which is associated with the absence of seizures. And the same can be said for our EEG results outcome variable. The better the EEG test results, the stronger the association with a healthy outcome, so not having a seizure. On the flip side, age and lower compliance to medication is associated with a lower odd of a healthy outcome, lower chances of having a healthy outcome. So the patient is more likely to experience a seizure. So lastly, I researched some diagnostic tests that I could perform for my logistic regression model, and I settled on the Hosmer-Lame show, which is right over here. So this is a goodness of fit of a logistic regression model. It compares the observed and expected frequencies of the outcome variable in subgroups of the sample based on the predicted probabilities from our model. A significant result indicates that the model doesn't really fit well and further investigation is needed. Since our p-value is below the 0.05 level, this means that it's not a great model for our data set, so we may be better off using the linear model. However, David Friedman states that statistical models should be evaluated in terms of their predictive accuracy, not just their goodness of fit to the data used to develop the model. So cross-validation and out-of-sample testing are really important methods to assess the predictive performance of a model. So the Hosmer and Leem show goodness of fit test really shouldn't completely rule out this logistic regression model for our data set. However, at the end of the day, I think I prefer the linear model for this specific data set. I think our results showed some more statistical significance, and yeah, all right. Well, that was model 3. Thank you. Had a great semester. I really enjoyed these modules. But yeah, thanks again.